Welcome to Rome Hack. When Giovanni asked me, like in January, to open this year's edition of the conference with a keynote speech, I didn't have the slightest idea of what I could talk about. You see, never been a fan of keynotes myself. I always preferred technical talks that usually give you a bit more substance, in my opinion. So I was in doubt for a while, and then it hit me. What if I tried something different? And so today I would like to do an experiment with you. Instead of the usual, perhaps even boring keynote, I'd like to talk about memory corruption bugs. I'd like to show younger generations, that's supposed to be you, that at least some of you, that beside those related to web technologies that you might be familiar with, other kinds of weird machines can be extremely fun to play with. So let's begin with a quick survey. Who among you has ever exploited a memory corruption bug? Please, let's have a show of hands. Okay, okay. I see a few hands. Good. And who has ever exploited a formal string bug specifically? These are a bit old. Okay, okay. We have some people. Good. Last question. Who has ever exploited anything on Solaris? Come on, I know. Ah, I see one hand. Hello. Oh, old timers. Hello. Okay, so regardless of your level of familiarity with these topics, I hope you will enjoy my last Solaris talk. So today I'm going to dissect a particularly challenging exploit, at least for me, that I put together and published a few months ago. It's a format string exploit that targets Solaris Spark systems. So it doesn't get much more old school than this. Of course, this is not going to be a crash course on Solaris Spark exploitation because we don't have the time. However, if you are interested in this topic, I encourage you to take a look at my article that it's about to be published in a major hacker magazine. Unfortunately, at the moment, I can't say anything else, but if you stay tuned, you will see that the article will be published, and more importantly, this major magazine that I'm not going to name will have a new issue very soon. And that's a great event in my opinion. Okay, uh, time to talk about Solaris. Solaris is a commercial Unix operating system that was developed by Sun Microsystems in the 90s and was later acquired by Oracle in 2010. It's one of the most successful, in my opinion, Unix operating systems. And you really could find, in the early 2000s, you could find it anywhere in all kinds of enterprises. A little bit like Windows is today. Uh, Nowadays, unfortunately, in my opinion, it's considered legacy technology, but it's still maintained, and it will be for a very long time, until at least 2035, I guess. But you can still find it in some critical environments, especially telcos. I've been hacking Solaris for quite some time. Here you can see my first and last release for this platform according to PacketStorm. And as you can see, they have a time span of about 20 years. I started hacking Solaris in the early 2000s because as a pen tester back then, as I said, I was encountering it very often, almost on a daily basis. And so I wanted to be able to hack into it to do a better job as a pen tester. To put things into perspective, the early 2000s were still the years of war dialing. We were still doing it. As a matter of fact, we should still be doing it also today, in my opinion. But anyway, back then it was still sort of popular. So we were still using ToneLock, we used Minicom, and we even still had X25 networks, even though they died shortly after, a few years later. What we didn't have were the amount of captured flags that you have today. And of course, we didn't have bug bounties. So hackers from my generation had to invent something else to pass the time. And this is how, together with some friends and co-workers, we decided to buy some old hardware on which we could install Solaris to play with it. Solaris can run on Intel, but you usually find it on the Spark architecture. Spark is an early RISC architecture, arguably the most successful early RISC architecture that paved the way to more modern RISC processors that you might be familiar with, such as MIPS and of course the ubiquitous ARM that's in everybody's pockets today. Okay, so we talked about Solaris, we talked about Spark, we just missed one thing. What the heck are format string bugs? Well, story time. It was the summer of the year 2000. After a couple of FTPD exploits hit the bug track mailing list, two authors, Lamagra and Tim Newsham, published the first white papers on this new attack class, on this new bug class, the format string bugs. And then the fun began. Everything was vulnerable. Beside the network services, also local set with binaries were vulnerable, even libraries. And everybody was writing exploits for these new fun bugs. But what are they? From where do they come from? Like many other bug classes, format string bugs stem from the laziness of programmers who, instead of writing this, they prefer to write this, saving time, effort, and 6 bytes of source code. But what's the implication? Well, if an attacker can control the string that gets passed to a printf family function this way, he or she is able to provide some special characters, some sort of metadata in the form of %d, %x, so the formatting directives, and influence the behavior of this kind of function. If you think about it, it's just another example of mixing data and metadata in the same channel. So it's a little bit of what happens when you exploit a SQL injection or other kinds of injection, or even what makes possible to exploit buffer overflow, either stack-based or heap-based. But in this specific case, if you control the format string, you can at least have an information leak because you can read the content of the memory. This is usually done via the %x, %d, or similar formatting directive that take parameters straight from the stack. So you can read the stack memory, and that's really useful, for instance, to bypass ASLR or other similar countermeasures. What may not be so obvious is that this little mistake enables an attacker to execute arbitrary code. Usually, not always, but that's usually the case. This is done via the %n formatting directive that's, with some tricks, enables you basically to write whatever you want, wherever you want in memory. And this usually leads to code execution, as we will see. As you can imagine, format string bugs are extremely powerful because they give you an information leakage primitive, they give you a write what where primitive, and they're very fun to play with, but unfortunately for us exploit writers, the fun didn't last much because they, as it turns out, are quite easy to spot by means of static analysis techniques. So they were quickly eradicated. Or were they? Please allow me to introduce our bug of the day. Sorry. In 2019, at Infiltrate in Miami, I told the story of a zero-day bug that was 18 years old in the Common Desktop Environment, or CDE. That is a software that's distributed with Solaris, among other commercial operating systems. CDE is a software that will be remembered fondly by all hackers who were active in the 90s or early 2000s, not just because of its looks. Yeah, that's a little bit too much of school, even for me, that CDE, if you haven't never seen it before. So not because of its looks, but mostly because it was ubiquitous. You could find it in all kind of Unix systems, almost all kinds, and even on non-Unix systems, you have it on OpenVMS, for instance. And it was then vulnerable. So as a pen tester, if you found a system with CDE, you could almost certainly be able to hack into it remotely or leverage some vulnerability to increase your privileges locally. So my talk, reminiscing of these golden days of unmitigated exploitation of CDE, inspired Marty, a young researcher from Spain who watched the talk and decided to follow my advice. And so he decided to take a look at CDE himself and see if he could find some new bugs. Of course, CDE is closed source, so at least that the one that's distributed with Unix. There's also an open source version that you can take a look at. So he reversed some binaries, and he eventually found one bug. Let's see if you can spot the bug yourself. I'll leave you a few seconds. So this is the decompile of the checkdir function of the dtprintinfo binary. That's a binary that's distributed with CDE that was plagued by, I don't know, many vulnerabilities in the past. So anyone can see where the bug is? Of course, it's in the highlighted line of code, the one marked with a vuln comment. That was too easy, but actually that was a little bit of a trick question. Only in this screen, I see at least 4 bugs. Only in the highlighted line of code, I see 2. There is a stack-based buffer overflow and a format string bug. This really was code from another era. Today, we're going to focus on the format string bug. As you can see in the highlighted line of code, the sprintf function parses the format variable that comes from the recdir environment variable. So this means that a local attacker who is in control of the recdir environment variable can pass an arbitrary format string to the sprintf function. And this means that it's game over, right? Well, not so fast. Took me almost 2 weeks to put together this exploit, which I know is not a lot compared to modern exploitation efforts. I'm aware of it. But in my experience, it's a long time. For me, it's a long time. I encountered many roadblocks and complications during the development of this exploit, and I came close to giving up a couple of times. So let's see what happened and how I overcome the difficulties. First problem I faced was the fact that, as I mentioned, there were 2 bugs, the format string and also the buffer overflow, and I wanted to exploit both of them. I was able to do that on the Intel architecture, no problem, but on Spark, I wasn't that lucky. Why is that? Well, as a general rule, exploitation on Spark is much more painful and fun than on Intel. Yeah, there's a little bit of masochistic thing in exploiting stuff. If you have done it, you know. In this specific case, the problem is related to how Spark manages the stack. Without entering into the gory details, suffice to say that if you have a stack-based buffer overflow on Spark, you cannot overwrite the saved return address of the function where the vulnerability lies. You usually are only able to overwrite the saved return address of the caller of the vulnerable function. This means that you have to survive 2 returns, 1 additional return compared to other architectures. Depending on your target binary, this might be easy, hard, or impossible. In this case, I'm not saying it's impossible, because probably it's feasible somehow, but it's definitely hard, because when you perform the overwrite, you overwrite also a lot of pointers, critical pointers that are used by the target program, and this is problematic because the target crashes, so you cannot really elevate your privileges. So I decided to solve this problem by completely ignoring it and focusing on the format string bug instead. Why not? Let's see, that's another example of the nice CDE interface. Let's see now a couple of prerequisites for our exploit. Well, first thing, as I mentioned, dtPrintInfo is a binary. It's a set with binary. And by the way, I have no idea why it's set with. There must be some reason, but I don't know why. I don't care, because that's the only reason why we are able to exploit it in order to elevate our privileges to root, so I'm not complaining. When you launch it, you see this interface that displays information about printers and print jobs and this kind of stuff. The prerequisite, one of the prerequisites for our vulnerability to reach the vulnerable code path is to be able to double click on a configured printer, like the one that you see here. If you have a configured printer on your target system, you're in luck, you can go on. But if you don't, then you have a problem, because as a regular user, as far as I know, you cannot configure a printer yourself. What you can do instead is to use an old trick, an old bug that's part of the bugs that I disclosed at Infiltrate in 2019, that basically can be used, among other things, to fake the presence of a printer. Of course, you need to have a system that's not patched. We don't have the time to see how this works, but if you're interested, you should check out my old talk. Going a bit further in my exploit code, here we set up the environment and some variables before we execute the vulnerable program. The most important thing to notice here is that we are using two buffers that with a lot of fantasy, I named buff and buff2. In buff, we are going to put our hostile format string that will exploit the bug. And in buff2, it doesn't really matter what's inside there. I put a lot of these. It's just a padding that's useful because, as a side effect, our sprintf, the vulnerable sprintf function, when it parses our hostile format string, it needs to write a lot of stuff on the stack, and so it might try to reach past the end of the stack, thus crashing our target program, and thus invalidating our exploit. So I hope you're still with me, because I think I see some puzzled faces, because now it's time for the hard part. In order to be able to turn our memory corruption into a nice, weird machine, we must be able to have a write what where primitive. So we must be able to craft a format string that's able to write wherever we want, whatever we want in memory. This is usually done with the %n formatting directive, as I mentioned. This is usually done like on Intel, on other architecture. Just this is abused to write 1 byte at a time. But this, unfortunately, is not possible on Spark, because that's another typical problem with Spark. It's a RISC architecture, and most, maybe all RISC architectures complain if you don't access memory at specific offsets. So you need to access memory with addresses that are all a multiple of 4. So you cannot address each byte separately. There are some tricks that can be used to bypass this and exploit this kind of vulnerabilities on Solaris, but for some reasons related to the fact that the vulnerable function tries to reach past the end of the stack, they weren't really applicable to this case. So what I did in desperation, after a long time of trying and debugging, is to figure out a possibly novel technique to exploit format string on Spark in order to write 1 byte at a time. I don't know, I haven't read about it anywhere, so maybe it's something new, I'm not sure. Let's see the code that implements this. I'm not going to comment this because it's, I don't know, maybe it's a bit too complicated to read if you're not familiar with C code. I would just show you how it works with the help of GDB. Sorry, spoiler, okay. Let's see, we have shellcode like this one, and we want to write it somewhere in memory. Let's see how the code that you saw earlier implements my technique to write the first 4 bytes of this shellcode. Oh, by the way, Spark is big endian, so you will see that the bytes in memory are represented in the natural order. They're not inverted like it happens on little endian architectures such as Intel. Okay, we write the first byte, the least significant byte, using the %n directive pointed to the target address. So far, so good. Then we use the %hn directive to write the third byte. Also, that's pretty normal. Then we use the less known hhn directive to write the most significant byte. But then we are left with a problem. How can we overwrite the remaining byte? There's no there's no directive that enables you to do that directly. So I experimented a lot, and out of desperation, again, I tried something that was not supposed to work, that is not supposed to work. I tried this. So as you can see, I referenced a memory address that was not a multiple of 4, because I added 2 to the base address. And so our program was supposed to crash with a bus error, but it didn't. It worked. So I don't know why. I don't explain this, but I'm not complaining. This is what enables our exploit to work. And this happens a lot. If you've written exploits yourself, you know that sometimes it just works. Maybe you don't feel like investigating the reasons why. So if you leave our exploit running, you see that it's able to craft all the shellcode in memory. We'll see shortly what the shellcode does. But first, we need the final piece of the puzzle. We need to decide where we perform our overwrite in memory, what we overwrite. So I turn to my old, with yellowing pages and all, Shellcoder's Handbook, published more than 15 years ago, in search of inspiration. And based on this book and on my experience, I identified a few candidates, a few memory areas that are good candidates for overwriting in order to hijack the control flow. Unfortunately, all of them seemed like dead ends. For instance, the PLT entries that are similar with GOTA entries on Spark, but let's not go too much into details here because it's a bit complicated. Anyway, they are like jump codes that get called when you call a library function. In the binary, they started with a null byte. So this was a no-go. We cannot use that in this kind of overflow. I even meddled with the function activation records, which is notoriously, at least in my opinion, a terrible target because it's not very reliable. They move a bit in the stack. I even managed to write a perfectly working exploit with just one small program. It works, yes, I published it. You can try it yourself if you have a Spark machine. But it works only when a debugger is attached to the target program. So that's not really useful in a real life scenario. That's another perk of Spark related to caching. So long story short, after a lot of dead ends, I noticed something. I noticed that libraries, so library binaries, not just regular executable binaries, also have a PLT section. And this PLT section doesn't start with a null byte. It's writable and it's executable. So it looks like a perfect target to me. If we take a look there in that memory area, you see that you have indeed code, that's executable code in Spark assembly. It basically implements some jumps, some branches to the code of the function that you call. Depending on the function that you're calling, it branches to that function. Okay, so coming back to our pseudocode, our plan is to exploit the format string bug in the highlighted line of code in order to overwrite the jump code in the PLT section of the libc of the string len function that gets called right after our vulnerable function in order to hijack the program control flow. But with what should we overwrite it? Well, we have two options, basically. We either overwrite the target of the branch, of the jump, or we can craft our shellcode directly in memory. I like to keep my exploits as simple as possible in order to keep them as reliable as possible, and therefore I went for the second option. But of course, we have one problem, the last problem, hopefully. We are limited to a 36 bytes override here. Uh, I don't know why. I don't know if it's a problem with sprintf or something else, but I really don't care. At this point, 36 bytes are more than enough for a shellcode. So I wrote this custom shellcode that you already viewed in a previous slide. Unfortunately, we don't have the time to see how it works, because shellcoding on Spark is really fascinating, in my opinion. But what it does is to set the setwidth bit on a target binary. As a matter of fact, to set all bits on a target binary on disk, in this case, the me binary. So putting everything together, we first create directory tree that enables us to reach the vulnerable code path. We create a symlink from the me file to the corn shell, the system-wide corn shell in the bin directory. Maybe that's not very elegant, but who cares? Everybody's root on the system now. Then we use the trick that I mentioned earlier to fake the presence of a printer, and finally we populate the environment and we run the vulnerable program. Let's see the exploit in action. As you can see, the corn shell has regular permissions. Then we execute the exploit. That's normal. The illegal instruction is normal. And then the corn shell is set with root, and we are root. Applause. Thanks. Yeah, that's very satisfying. After 2 weeks of work, it is. So hard to believe, but 21 years almost to the day have passed since that fateful summer when the format string bugs were first disclosed to the general public through the bug track mailing list. And it's also hard to believe that they weren't completely eradicated, because as I mentioned, they should be quite easy to spot just by looking at the source code, even with automated means. But unfortunately, or fortunately, depends on your perspective, these kind of bugs have a way to creep back even into modern code. Just a few months ago, in June, this bug made some news, made the news. So basically, if you had an iPhone and if you connected to a Wi-Fi network with this kind of SSID, which is obviously a format string that exploits something, your iPhone, the functionality, the Wi-Fi functionality of your iPhone will be bricked, basically, until you do some recovery, but it's quite complicated. So as you can see, these kind of bugs can still affect even modern code, such as the iOS code. The specific bugs that I told about today were fixed by Oracle in the aftermath of my recent vulnerability disclosures. There was like a general cleanup of CDE code that's still distributed with Solaris 10. However, I have the feeling that there are still many bugs lurking just beneath the surface, just waiting for some inspired hackers to find them. That's just my idea. With this, I think I'm done. I'm done with the talk, and I'm also, I guess, done with Solaris. Took me a while, but I think I will do something else from now on. I would just like to leave you with one last thing. As an InfoSec professional, if you all remember one thing out of this weird keynote speech, it should be this. Hack the planet. Seriously. That's the moral of the story, Seriously, do a little bit less of whatever you do in your day job, do a bit less of Zoom, do a bit less of Outlook or PowerPoint, whatever, and go get your hands dirty, write some actual code, and have fun. That's my message to you. So thank you very much, and enjoy the rest of ROM Hack. Thanks.